Hi everyone. So today I will talk about the fine-tuning methods for text-to-image models. And modern text-to-image models such as Stable Diffusion, DALL-E 2, Imagine, Karlo is a major breakthrough in contemporary generative AI topic. And this is a very crucial to fine-tune them, to adopt them to the different use cases. So today I will present several fine-tuning methods. We'll start from the discussion about the text-to-image model's high-level architecture. After it, we will talk about models fine-tuning concept in general. After it, I will present the 5 different methods for the fine-tuning. We will summarize them in a summary, and then we will perform the Q&A. So, first of all, let's talk about the model's architecture. Yeah, this is a very large amount of different text-to-image models on the plate for now, but all these models have shared and very common high-level architecture. So in this slide, you can see the general architecture for all text-to-image models. So we're starting from the text. We're feeding this text to the text encoder. Typically is one of these large language models, such as CLIP or something like that. After it, we will get the text embeddings. Yeah. And feed these text embeddings to the image decoder. In a majority of cases, the image decoder for now is a diffusion model. And finally get the image. Yeah? So this is a high-level architecture of almost every text-to-image model. And our main goal is that, for example, we want to teach our text-to-image model, yeah, our pre-trained text-to-image model, to generate this particular kind of dog. Yeah, this is a very specific type of dog that is not represented in a text-to-image model, and we try to teach this model to identify and we're able to generate this particular kind of dog. Yeah, so we have a new data set with a new concept, this dog. Represented as image text pairs. Yeah, there's several image text pairs. Yeah, you can see that we are feeding it to the model and try to teach this model to generate this dog in different contexts. Yeah, it's not necessarily to be some subject-driven concept. So it can be some style or even some large group of concepts, so it's not necessarily the one, but for simplicity, let's assume that in this presentation we will talking about this simple case. Okay, so the next slide is about that. Okay, we have this new data set with a new concept in it, and the most simple setup with the for training of this model, we will have this shape. Yeah, so we have a new data set where we get from this new data set the text and image, yeah, feed the text to the text encoder, get the text embedding, feed to the image decoder, get the image, calculate the loss between images, and backpropagate it to the image decoder and text encoder respectively. Yeah, so this is the simplest possible setup, but unfortunately, this type of fine-tuning it's not working very well with these contemporary large models because of various reasons. Yeah, we have 5 large reasons why this particular case is not working for these large models. So the first problem is a dataset size. So typically, this text-to-image models is trained on very large data sets. Yeah, very, very large. At least 500 million image pairs in general. Yeah, this is one of the smallest number in the industry. So this and for retraining it without the overfitting, we need at least the same magnitude of data. Yeah. So the second one is a quality. Yeah, this is a quality level of results after fine-tuning. In this case, if we just give our data and feed it to the network and train it, in almost every case we will have pretty pure quality because it's instantly overfit this data set, because typically even in a commercial scale industry, the data set is not that large. Yeah, so for example, the 10 million is a very small data set for this type of models. And the third problem is forgetting. So this is a very specific type of overfitting related to the large models. It's called catastrophic forgetting, when we're trying to teach the model the concepts and it forget everything that it learned before. So if it's a pre-trained model and we have a very large amount of concepts encapsulated in it, and it just forget all these things and become a very weak model. Yeah. So this is an amount of how much model forget after the fine-tuning. Yeah. Of course, it is the speed, because for training of this type of models, especially with the large data sets, require a very large amount of resources and very large amount of time. And last but not least, this is a memory consumption, because the storage consumption. This is a pretty big problem in the industry, because these large text-to-image models, in average, is very, very large. So it's take like 5 and 3 gigabytes at least. Yes. So if you are trying to train different models for different cases, you will have a very large amount of models with this amount of space, yeah, and the memory storage consumption will be very high. So, so this simplest method is not working for our case, and we're defined 5 different metrics how to evaluate the further methods. So let's go to the methods. So in general, we have very large amount of different fine-tuning methods. It's a very hot topic in a generative AI for now, and almost every day the community has created something new in this topic. So, but for today, I will discussing the 5 different topics, 5 different methods for today. And the first one is regularized fine-tuning. So the idea of regularized fine-tuning is very easy. So they try to avoid this forgetting. Yeah, this is one of the major problems. So the first target to solve for the scientist will be this forgetting part, and they design a very simple system when they just add some regularization dataset to our new dataset. Typically, this regularization dataset is sampled from the original training set of the model. Is, for example, for the Stable Diffusion, this is a sample from the lion, yeah? And mix this regularized dataset with the new dataset and train this whole model on this both datasets simultaneously, yeah? So in this case, it's obviously will prevent some overfitting and forgetting. And in general, yeah, this setup works, and it's several implementation in a public community. So one of the famous one is every dream setup that you can find on GitHub. In this case, this particular method is working only with the middle and large size datasets, because it's still large-scale fine-tuning. Yeah. So, but this large data set is not that large that before. So, for example, it starts working with this 10 million, 5 million, etc. Yeah. The quality is very high because it's still high scale, large fine-tuning of the all parts of the model. Forgetting is still there. It's impossible to avoid the forgetting at all. So this is a forgetting some parts, but it's very few things. Yeah. The speed is slow because at least we are adding some new part of data to our data. So the data is at least doubled in this case. And yeah, it's obviously that we still have slow training process. Yeah, and the storage is still high because we are fine-tuning the text encoder and image decoder, and we need to store it after the retraining. Yeah, so this is a first setup. Before we will go to the next ones, we need to introduce one more concept to our data set. So we need to add to our concept the special keyword that we call unique identifier. In this case, is this brackets V. Yeah, and in this case, you can see that we are if we want from a model to generate this particular dog, we're specifically specify this dog with this V unique identifier. The idea is that if you want to teach models something very specific and the distribution is much smaller than the original distribution of model, you can fix the actual part of the latent space with the introducing of special keyword for this data. Yeah, so it's obviously narrowing down the possibility of the system in terms of like this special keyword can be very wide because yeah, in this case it's just useless, but it's narrowing down the use case, but give us several advantages that I will present in the next slides. So the first system that use this unique identifier as an advantage is Dreambooth by Google. So the idea is following. This is a very similar setup to the regularized fine-tuning. The difference is only these two things. Yeah, the first thing is we're introducing this unique identifier, yeah, and attaching it to our data set in some sort of way. So typically it's in the beginning of the text, yeah, or in the end of the text. And replacing the regularized data set with more specific data set. In this particular case with the dog, we're replacing our regularization data set with a data set of dogs, but not this dog that we're trying to learn. Yeah, so the other dogs. And all other things is pretty same to the regularized fine-tuning. So these two things is allowing us to have this Dreambooth model that typically have following characteristics. Yeah, the dataset size that is required for the training is small, and it's not supported the large dataset. It's it's not working for the large datasets, and typically after the hundreds of images, it started doing some artifacts. So this is working only for small datasets because of this unique identifier and some specifics of the construction. The quality is very high. So in industry, this is one of the good quality methods for fine-tuning. The forgetting is a few things, yeah, still not very much, more than in a previous case in general, but less than the fine-tuning itself, the raw fine-tuning. Yeah, the speed is a middle because we still have some additional data set in this case attached to the model. And the storage is still high because we fine-tune the text encoder and image decoder and need to store the weights. Yeah. So the next major topic that about the fine-tuning, this is the textual inversion. Yeah. Textual inversion is a very interesting idea when we're trying to shift this idea of fine-tuning of the models to fine-tuning of text embedding. So the idea is following, where instead of training the large models, this text encoder and image decoder, we're trying to optimize the text embedding of this specific unique identifier. So what this means in terms of latent space. So in this case, we're just assuming that our text-to-image model is general enough to capture all the information in our new data set, that basically we're assuming that this model is already contains this particular type of doc in it, but we just need to find it. So this is an actual idea. So this optimization of this text embeddings is just searching in a latent space, basically. So we're trying to find this concept, our doc concept, in a latent space of the text encoder. So this is one of the most interesting one, because it's it's some paradigm shift from the other two ones. So in this case, this works with the small data sets, even with very, very small. So we'll even work with the one image. The quality is still pretty high, slightly less than Dreambooth, but still high. The forgetting in this case is very good in terms of we can't forget anything by definition in this case, because we're not training the text encoder and image encoder. It's just impossible to forget something. So we're just introducing and just finding the concept in the model. So in this case, we forget almost nothing. So in terms of speed, it is a middle. So middle because you are still need to forward the actual text encoder image decoder. So this is just time consuming because this is a large model. But yeah, it's significantly faster than the previous one, because you just need to update the gradients only for this text embedding. And the memory consumption is very low, and in this case is, I think, the lowest one from our today presentation. So it's very, very low. It can even take several kilobytes. It's very, very low amount of data to store. This is about the textual inversion. So the next one, this is a LORA. So low rank adaptation. The LORA is not something new in a machine learning and deep learning itself. So this is a pretty old method for training optimization, for the optimization of training of large models. The only difference and only novelty of the method is that the open source community adopt this low rank adaptation to different text-to-image models, such as Stable Diffusion, etc. So in this case, they introduced two tricks. It's very similar approach to the raw fine-tuning, but instead of training the text encoder and image decoder, we're just adding new layers using this residual connection trick to the models, and train only these layers. So we're freezing the entire text encoder, entire image decoder, and train only our added layers. And in this case, it's obvious that we are adding the count of parameters. So we're just adding some layers. It means that we are multiply the amount of weights, and we will have the pretty large weight matrix. So in this case, the final and most important trick is that they try to they actually factorize these weight matrices to the two matrices. So this is a conventional matrix factorization, and using some of the methods for matrix factorization. So and in this case, they try to approximate this weight matrix with the two low-rank matrices. Yeah, so in this case, you can see this is a 4x5 matrices. We are factorized it by 4x2 and 2x5. In this particular case, we don't gain very much amounts of weight after this operation because, yeah, we are just just gain only 2 weights. Yeah, because the 5x4 is 20 and this is 18. Yeah. So, but in a real case, this weight matrix is way larger, and the factorization is gain for us a very large amount of weight. So basically, in this case, we're decrease the amount of weights very dramatically. Yeah. So this type of fine-tuning is working with almost any data set. So it supports the small one, the large one, the middle one. So it's just depend from your rank parameters. So you can adapting your actual setup to capture the data, no matter the size. Yeah, the quality is a middle because we're restricting our generation possibility 2 ways. So we are train only the audit layers, but also we're decreasing the amount of weights significantly, and this is of course lowering our quality in general. It's not necessarily bad quality, but this is less than in the previous cases. Yeah. So about the forgetting, it still forgets something, but not very very much. So these are again few things. And in terms of speed, it's very fast because you are doing this trick with the low rank adaptation. So you are optimizing just very small matrices, and this is typically much faster than the training of the actual 2 models. It's very dependent from your rank, but actually, yeah, it's give us the acceleration. And the storage is low because you need to store only these 2 factorized matrices on the disk. So this is 2 very small matrices. Yeah, in this case. Okay. And the next one, the last but not least, this is the very similar idea to the LORA, but the difference is that we're replacing all these things related to these weight matrices with some neural network that we call Hypernetwork that is trying to predict the weights for these audit layers. Yeah, and we're training only this Hypernetwork. Yeah, this method is much flexible than the LORA, but also this method is much more complicated in terms of maintenance and in terms of finding the good optimal parameters, because you need to design this Hypernetwork typically, and sometimes it's not easy. But in general, it's obvious that you can create the Hypernetwork that is much more regularized in terms of weight generation than the method LORA that I presented previously, because you can add some losses to this Hypernetwork to prevent some weight explosion, etc. Yeah, so you have a more fine-grained control in this case. And this method is also support any dataset type. It's just dependent from your Hypernetwork size. The quality is the same to LORA. Forgetting is also the same, so you are forgetting few things. The speed is a middle, because in this case you are optimizing the network instead of optimizing the just weight matrix. So this is some computational overhead typically in the Hypernetwork. And the storage is also middle, because you are not because typically the Hypernetworks is slightly have more capacity and more weights than the low rank weights before. Yeah, so this is some middle case. Okay, so this is our summary. So you can see all the methods represented together and all our metrics. And you can see that in general, we don't have the clear winner there, because each model is somehow unique and support different type of things, and basically you can use each of them for your specific use case. It's very dependent from your particular use case. Yeah, so all these methods is pretty useful, and all this method is used in a community and in an industry. So but yeah, you can see some models have some weaknesses and advantages. Yeah, so you can compare them and choose the best one for your use case. Yeah, that's all from my side. So you can from the Q&A. Okay. Thank you. So the questions. Yep.
My question is related to the regularized fine-tuning.
Yep.
We were using two data sets, right? We were taking some part of the training data set.
Let's go to the...
We were taking some part of the training data set and mixing it with the new data set, right?
Yes.
And for generating new images, the image decoder takes in account the gradients of the text embeddings, right?
Yes.
So if we add some, I don't know, other images rather than the dog images,
yes,
wouldn't their gradients be too different? Wouldn't it kind of mess up with the generating process?
Yeah, it's a very good question. This is typically controlled by this regularization loss weight. Yeah, so you can, if your data set actually is very different from your new data set, but you still need to preserve these parts of the distribution of the original text encoder. For example, you need to add the dogs, but you want to make sure that all other parts of the distribution of the original model is not harmed. You can add the very large amount of data from the original training set, from this line data set in the case of Stable Diffusion. It's possible, but in this case, you just need to do some tricks in this regularization loss. So you need to tune the weight and maybe balance these two data set in a batch. For example, you can create your batch based on the equal number of samples from this and this data set. Yeah, you can do the tricks to avoid the ignoring of your original concept that you try to learn.
Can we also control the values of gradients, like make the gradients, the directions of the new datasets images gradients bigger?
Yeah, sure. You can control it with weights. Yeah. Of course.
Thank you.
Yeah. Yes.
What is about overfitting of? What is about overfitting of that model? Because I know that dataset size is small. It's actually 10 or 10 samples. And is it true that the quality will be high because of the overfitting on that dataset that you are giving to him?
Yeah. In case of Dreambooth, our magic trick to avoid the forgetting is actually this unique identifier. So the idea is that if we are fixing the specific part of the distribution with some name, we're most likely not harm the other part of the distribution. This is not exactly true, so this is an assumption. But in general, this works pretty well. So in case of Dreambooth, the overfitting is still there, so you can see that this is a many things, not a few things. Yeah, this forget the many things. Yeah, but this introduction of this unique identifier is typically prevent us to to harm all other parts of the distribution just because we're trying to optimize specific place of the distribution. Yeah. So this is just our magic trick that help us. But yeah, Dreambooth is not very good as a general fine-tuning method. So you can't fine-tune the text-to-image model with Dreambooth to achieve some very generic generation things. Typically, you are trying to learn some specific concept like dog, like just subject-driven concept, or you are just trying to learn the style related concept. In this case, it's somehow works. So it's in the internet you can find a very large amount of different models created by Dreambooth, and for this particular use cases that they work pretty well. But if you are going to some specific parts of the distribution, you can find that basically they forget some things from the original distribution. So this is a method to add some small concepts to the model. Yeah.
And is it fair to compare this model with the other ones, such as LORA or Hypernetworks?
No. The idea is following. You can see in the LORA and Hypernetworks and in a regularized fine-tuning, we don't have this unique identifier thing. So it's not necessary to. This is a much more generic fine-tuning methods than the Dreambooth and Textual Inversion. Yeah.
Do you know about Lens AI? Is it similar? Is it work similar as Dreambooth?
Yeah, they use Dreambooth to personalize your avatar. Yeah, so they actually use Dreambooth. Yeah. Yes.
Can you talk more about this identifier, because I don't understand clearly what is it, because is it a word? Or?
Yes, this is a special kind of word. So this is a specific trigger word that we are giving to this text embedding, and yeah, this is a very specific word, and typically is some artificial word, because if we are choosing some real word in this case, for example, if we are just assume that this is a dog, yeah, just assign to this concept the dog keyword, it will be a problem because you will intersect the original distribution of Stable Diffusion, for example, yeah, and you will have some interconnected associations in the model, yeah.
And it's not the title or label, it's doggy.
No. This is some artificial word. Typically, this is one of the most popular one. This is SKS. Yeah, this is a very rare word that is not appears in real sentences, and they give this special keyword to this specific concept. Yeah. This is some artificial word to avoiding these random associations in the model. Yeah, this is some artificial word, and this type of words is also very common. So you can just write something with brackets and some letters, etc., and this works. Yeah.
Okay, and it's a good idea to take not only one identifier. You can make it.
This is a much more complicated situation when you are trying to teach your model to identify several different concepts. It's possible, of course, even with the Dreambooth, but this is a much more complicated case. Yeah, this is you need some more research in this case, because sometimes several concepts can't be distinguished from each other. Yeah, and this can be a very mess. Yeah, sometimes. Yeah, this is why typically the community is training this Dreambooth model using only one keyword. Yeah, so you are just add the one word and one concept and just it. Yeah, because in other case, in a multi-concept way, this is a much more complicated situation. Yeah, but it's possible. Yes, definitely.
Can you go back to the LORA?
Yes, sure.
Here, by this low-rank approximation, does this only give us optimization in terms of speed and memory, or we get better?
Good question. Yeah, this also give us the regularization because we're lowering amount of weights, and this means that we're have lower chance to overfit, and yeah, this is some sort of regularization. Yeah, and this is also affect the quality. Yeah, this is true.
Also, one question. We had different speed for speed in terms of. Can you go to the last slide?
To the Hypernetwork.
No.
Yeah, this one. Okay.
This one. The speed of the regular fine-tuning, regularized fine-tuning and Dreambooth is different. Yes. So what's the reason for that?
Yeah, it's just the difference is because the Dreambooth is working with the small data sets. This is just difference because of the Dreambooth is supported only the small data sets. Yeah, this is just because the data set size and the speed is correlated things. Okay.
And which one would you recommend if we are dealing with ultra high resolution?
Okay, yeah. In this case, if you want to generate, in general, all these methods is working with any resolution in general, but the model itself is typically have some base resolution that is trained on. And I think the regularized fine-tuning is one of the best one for the generic case in terms of like in a regularized fine-tuning you have more control over your training, and in this case I think you will be able to increase the resolution more easier than the other ways, because for example for the textual inversion it's typically it's not very easy to change the original resolution. For the Dreambooth it somehow works but not very well. For the LORA and Hypernetworks, since I think this is a second and third one. So the first one I will recommend the regularized fine-tuning. For the second one LORA. For the third one is a Hypernetworks, because yeah, this is a most generic three ones. Yeah, but the regularized fine-tuning is the most generic one, and yeah, and produce can you have very fine graded control over your fine tuning, so you can change the aspect ratio of the model itself even with this method is possible.
Yeah. Also, one more with regards to deployment, like automated CI/CD.
In this case, all the similar, just the difference in the storage phase. So, because this is a training method, so fine-tuning is a training phase. Yeah, this is not related to the inference, but the storage can affect your deployment a lot, because yeah, sometimes it's not easy to have very large amount of storage. Yeah, so. In this case, it's only the storage affects the deployment in general. Yeah.
Anything that we can train with Dreambooth, we can do it with textual inversion?
Almost everything. The only restriction, the textual inversion, is sometimes not as powerful to capture this concept. Sometimes you just don't have this concept in your original model. Yeah, in this case, Dreambooth can learn something, but the textual inversion can't. Yeah, because you can't find this if you don't have this in a model. But this is typically it's very rare concepts. Yeah, because this is very large models and they're trained on very large concepts. But yeah, sometimes it happens. Yeah.
So for faces, for example, the textual inversion also works.
Yeah, it works, but I think, it works, but slightly, I think, worse than the Dreambooth. because yeah, faces is some specific concepts that, for example, Stable Diffusion is not learned very well yet. Just not represent good faces in it. Yeah. Yeah. Yep.
What are the vectors of these models? What kind of model?
Can be everything hypothetically, but yeah, in a majority of cases, it's a Stable Diffusion. Yeah. So, but it's possible to adopt these models to the other models. But the only problem is that, for example, DALL-E 2 and Imagine is not open source. But for example, there is the Kakao Brain is publishing this Karlo model that is open source implementation of DALL-E 2. And yeah, these things is work with Karlo. Yeah.
Can you open the textual inversion slide, please? I'm not sure that I have the question, but I need to think.
Well, I have a question about LORA. So what's the intuition behind searching for weight matrix and low rank form? Is there any good intuition, or is it just...
I think it comes from this LORA thing is very old. So this is the first, if I remember correctly, the first usage of this low rank adaptation for optimization purposes is starting from these large language models. So yeah, this is just intuition that if you will factorize this weight matrix to the to smaller ones, you just give the speed up.
Are there any studies of how large the range has to be, or?
Yeah, it's very interesting thing that the speed is actually yeah, the only thing that you affect with this rank thing. So this is yeah, the speed and the storage, yeah, in the main cases. So you can this is a large trade-off, yeah, between three different things. So the first thing, this is your dataset size, that is represent your amount of new information that you try to inject to your model, and between the speed and storage things, yeah. So typically the method to find the correct rank is you are trying to get the highest possible rank, that the lowest possible rank that is can overfit your data, and iteratively try to decrease it to achieve the speed and storage. Yeah, so this is a logic, the typical logic for finding the rank for this case. Yeah, so.
Thank you.